So that's not like.
Yeah. Or you just don't.
It's still there.
Right?
Only this is not. HDMI cable look like missing. Yeah. It's not working. This
Kind of cable do you use?
HDMI.
I have like HDMI to USB-C adapter, if that works.
No, I have that.
Oh, you have that?
Yeah. The problem is it's. It looks like the screen isn't, the cable isn't working, so. Have to go for another cable. I saw one in here, but it's.
Yeah. Okay. Higher expectations. Let's say upgrades is a big thing when small positive. It's big. And then it seems unfortunately this changes. I get it. Actually, I'm not judging. It's judging. Not everything. It's not. It's like. No. I don't know.
Good. Let's hope. It works.
That's not.
Maybe you are.
No, I just believe that even if I get everything straightforward, it's fine.
Yes. Awesome. Okay. Hopefully we can get started now. Very good.
Yeah.
I mean, just like I thought, it's the cable with the red connectors. I have to like steal them and keep them myself so that nobody takes them away. Okay, let's get started today. After a little bit of a delay, so I just want to make a quick announcement. We will have the first quiz next week. It'll be a short, reasonably short, I think, quiz, 40 minutes or so in class next Friday. The topic covered is basically qubits and block sphere. And the homework that you're doing right now on the tutorial will feature strongly in the quiz. So please work on that and finish it. I think it's due the day before the quiz. So you should definitely be working on it anyway. So yeah, and the closed book, closed notes will give you all the formulas you need on the exam sheet, the quiz sheet. But please bring a calculator. I don't think there will be too many numerical answers, maybe one or two, but it's good to have the calculator in case you need it. So roughly about 9 or 10 questions. Don't worry, each question shouldn't take you too long to answer. But some of them do have multiple parts. And so it'll be a mix of like multiple choice and short answers. Okay. All right. Any questions about the quiz one? All right, let me get back to linear algebra that we were discussing in the previous class. And we introduced the dot product. So I'll just quickly remind you of that. We have two states, psi and phi, with those two column vectors. Then the inner product is defined as the conjugate transpose of phi, which is the bra vector of phi, times the column vector psi. And that, of course, is just a number, which is C star A plus B star B. And then, as you may recall, we did an example where we talked about finding the coefficient of the qubit state psi along some basis state, 0, for example, by taking the dot product, which is like the projection of psi onto the basis state. So that was psi projected onto 0, which we write, of course, as bra 0 psi ket. So that is 0 psi bracket, right? So, and I wrote it on both sides here. One is just the algebraic expression. We take that bra vector and we move it through the expression. So I get A times this plus B times that. And then on the left-hand side, I'm showing you what it looks like in matrix or vector notation. And then when you calculate by using the rules of matrix multiplication, you get A on the left-hand side and of course A on the right-hand side, because 0, 0, that product is 1, and 0, 1, that product is 0. Okay. And we did that for the one state as well, and we found that psi 1 is equal to B. Okay. That is 1, the psi projected on the one state is B. So since psi is equal to A times 0 plus B times 1, B ket 1, now A is shown to be the projection of psi onto 0, B is the projection of psi onto 1. So we can rewrite this entire expression as psi equals projection of psi onto 0 times 0 plus projection of psi on 1 times 1. Okay. Very simple. And the components, these coefficients, of course, by taking the norm squared of these coefficients, we get the probabilities to be in the basis state 0 or 1. Okay, that's just the usual rule that we have in quantum mechanics, that when we find that component along 0 or 1 or any basis state, we take the norm squared, we get the probability. So norm squared of our dot product of psi with 0 gives me the probability. And now, of course, what we want to do is to try and use this technique, not for the states 0 and 1, which are fairly easy. We could have just read it off from the superposition or from the column vector. That was easy, right? It was A, B. So you know immediately the component along 0 is A and component along B is 1. Component along 1 is B. You didn't need to do any real algebra to do it, but it was good to write it down so that you saw how that comes about. Now we'll actually make use of this to project onto any other basis state. By exact analogy with the 0 and 1 expression that I showed you on the previous slide, we say that the state psi equals projection of psi onto the plus state times the plus state, plus projection of psi onto the minus state times the minus state. Right? Simple enough? Everybody agree with that? The analogy, everything is clear? Okay. So, of course, we should do it for one state to see how it works in both of the formalism. So the first formalism is I want to take psi and project it onto the state 0. The state plus. The state plus is of course 0 plus 1 times 1 over root 2 on both of them. So here what I've done, I skipped a step here, sorry. So normally we write ket plus is 1 over root 2 ket 0 plus ket 1, right? And I've just taken the bra of that, okay? Which is, because there is no complex conjugate here, everything is real numbers for 1 over root 2, 1 over root 2, it just stays as 1 over root 2 times bra 0 plus bra 1, okay? And then of course, here's our psi, state psi, which I just transferred over from here. Okay, so let's do that in both ways. Phi equals root 3 over 2, 0 plus 1/2. Oh, sorry, started writing. Okay. One of them couldn't reach it. Okay, so psi equals root 3 over 2 times 0 plus 1/2 1, state 1. And our state plus is of course 1 over root 2, 0 plus 1. And we have to find the projection of plus on psi. The old way is just to find it using this technique. And we'll do it that way just to make sure once again. So that is, I take this 0 and I move it through all of this component. So 0 ket with 0 is 1, right? And 0 ket with 1 is 0. So that term vanishes. So we only have the term 0, 0. Okay. And the coefficient in front of that is 1 over root 2. And the coefficient in front of this is root 3 over 2. Yes. And then similarly, 1 on 0, that coefficient, that bracket is vanishing, right? And then 1 with 1, that bracket is 1. Okay. So again, we get plus 1 over root 2 times 1/2. Okay. So our answer should be root 3 plus 1 divided by 2 root 2. Okay. That's our answer using the old technique. Now with the linear algebra, we should also be able to do the same thing. So the plus state written as a column vector is 1, 1, right? And our state psi is root 3 over 2, 1/2. Everybody okay with this? And then state plus so now plus and psi, I want to find that. I find 1 over root 2, and now I need to, what do I need to do to this 1, 1 to make it into a bra vector? Yes.
Transpose it.
Transpose it, as well as something else. Transpose is
Well, you would transpose and then take a conjugate, but they're both.
exactly. Excellent. Yes, they are both real. So we don't need to do anything, but if there was a complex number, you would take its conjugate. Very good. Thank you. And then times our √3/2, 1/2. Okay. And this we can find using the rules of matrix multiplication that I showed you last time, which is this element multiplies this element, and this element multiplies this element, and add them together. Okay, so that's 1/√2 times 1 times √3/2 plus 1 times 1/2. So again, we get √3 plus 1 divided by 2/2. Okay. So now the nice thing about matrices is that there's lots of computer code that you can use to do that rather than having to code in some algebraic system like the one that we were doing earlier. So we can easily code this. Any questions on the workout calculation? So that's easy enough. I did this now for the minus state. We just did the plus state. So I'm repeating that for the minus state with just Python. Okay. So I just import in the usual packages for numerical manipulation in Python. And then I just define two arrays, psi, and then the minus state is just 1/√2 and minus 1/√2. And then I just use there's a function in NumPy called Dutt, which allows you to just calculate the dot product, basically. I made one small mistake here when I wrote the code. It should be minus, comma psi, not psi, comma minus, but it doesn't matter because they're all real in this case. But it could matter if they're not. So please fix that when you write the code yourself. Okay. And the answer is this. Okay. And if I then calculate by hand, the R on paper, what this value should be, I get that the actual answer should be √3 minus 1 divided by 2/√2. We got √3 plus 1 over 2/√2 for the plus state. So for the minus state is √3 minus 1 over 2/√2. And these two answers agree with each other. So you see, it becomes now very easy to calculate much bigger sort of, we'll see soon when we go to 2 qubits or higher, these matrices just become bigger. But so it becomes harder to do the calculation by hand. But the coding into something like Python or Mathematica makes it much, much easier to do these calculations. Yes?
Can you elaborate on why order matters for 25?
That's because it takes the complex conjugate of 1. The NumPy function
NumPy
does that.
Wow. Okay.
Yeah, exactly. I don't know how many people are familiar with NumPy package. Most of you? Okay. There's also Mathematica. So if you're more familiar with Mathematica, I can give you some Mathematica code as well. And I might show you some Mathematica code later in the slides as well. So we'll see that. Okay. So if I'm given any two orthonormal basis states now, so we chose plus and minus because those are familiar ones, but we could generalize to any two orthonormal basis states, alpha and beta. And we can find the projection and verify the probabilities, find the probabilities as well, right? I just take norm squared of those coefficients. I'll get the probabilities, excuse me. And that's just, again, an exact analogy with what we wrote for plus and minus. We write it for some new set alpha and beta. The only requirement, as you know, is that alpha and beta should be orthonormal. Does anybody remember what orthonormal means? Yes.
On opposite sides of the block here.
Correct. But what does it mean in terms of the inner product? Can you
Zero.
between two of them is 0 and between any one of them?
Yeah. We got one for one.
Yes. Exactly. Very good. Excellent. So, yeah, and again, we say alpha psi is the projection or probability amplitude. Yeah, so there are many words that will be used. They all mean the same thing. The coefficient, the component, the projection, probability amplitude, overlap. All of these mean the exact same thing. Okay. Between the states alpha and psi, this is how we'll always find it through this inner product. In fact, we can generalize this not just for qubit states, but also for any other kind of quantum state. This is how all of quantum mechanics is written. So by learning this language, you're learning the language of quantum mechanics. Except that we'll have to generalize it when we get to things like if instead of like choosing basis states of like 0 and 1, if you want to choose basis states of position or momentum and so on, then you can start to do that as well. And then you can learn about infinite dimensional quantum spaces and so on, Hilbert spaces and so on. But the basic idea is exactly this. Okay. Okay, any other questions before I move on to the next topic? Okay, if you have any, don't hesitate to ask. All right, now we're going to ask about quantum gates. Because remember in the earlier lecture, last class and the class before, we were learning about quantum gates in the language of Kex, right? Now we want to put that in the language of linear algebra, and we'll see that things will become easy to manipulate those quantum circuits and so on. Okay, so let's start with our initial definition of a gate. Remember that gate definition is just you acting on the state 0 takes you to some state, new state. That new state is defined as A times 0 plus B times 1. Okay, and then we also need to know what U does to the state 1. Okay, since U acting on the state 1, let's say that it makes it into C times 0 plus D times 1. Okay. And now in our new language, we know that the state that is A times 0 plus B times 1, I should replace 0 by the column vector 1, 0, and 1 by the column vector 0, 1, and then add them together, which gives me the column vector A, B. Right? Everybody okay with that? And similarly, if U is acting on the state 1, it gives me the column vector C, D. So from this, we can make a convention that the first column of my gate U will be whatever is obtained by taking U and acting on 0. And the second column of 1 will be whatever is obtained by taking U and acting on the state 1. So you see, I just taken those two column vectors, put them in the 0 and the 1 column of U, and that is the definition or the new, or we can say the matrix A, C, B, D. This matrix now represents my gate U. Okay? Because it gives me on any linear combination, which I'll show in a second, if I take any linear combination, okay, or let's also make sure we can go the other way. So now that we have this definition for the matrix A, C, B, D for U, let's now act with it on some state. Make sure we recover reasonable answers. U is now the matrix So let's make sure that U acting on the state 0 gives me back the column vector that we want, which is U is acting on the column vector 1, 0. Okay, that is A, C, B, D acting on the column vector 1, 0. So just like we said before, the rules of matrix multiplication, which is take this A acted on the multiplied by that element 1, take this C multiplied by the element 0. So that gives me on the top row A, and then in the bottom row, same idea, B acting on the state 1 or B times 1 and plus D times 0. So that gives me again B. So that's right. That's what we want. We said we started with that definition that U acting on the state 0 gives me the state A times 0 plus B times 1, and that's what we have recovered by taking U and actually doing the rules of matrix multiplication with the column vector 1, 0. And okay, I won't carry through, but you can clearly see if I do it with A, C, B, D acting on 0, 1, I'll get the column vector CD, which is what we want. And of course, you should check, we'll check now, a couple other situations. Let's do A, C, B, D acting on now the plus state. The plus state I just wrote for you in the previous, so that's 1 over root 2, 1, 1, right? That's what we had just done in the previous example. So now, again, by the same rules, I get A plus C divided by root 2 and B plus D divided by root 2. See how simple it becomes now to just find the action of the gate on any state, not just 0 and 1, by simply following the rules of matrix multiplication. Okay. And you can do for minus, clearly, the only difference will be there'll be a minus sign over here. Okay, so plus or minus, depending on whether this is plus or minus 1. Okay. So now I can generalize. Now I'm going to act on any general state, psi. So psi is the state E times 0 plus F times 1. Okay. What do you think? What's our answer? What's on the top? Yes?
AE plus BF.
And maybe you can tell me the other one.
E plus D.
P. What's the second one? E plus D. Very good. Exactly. Got it. So already now we can do any gate U acting on any state psi with this rules of matrix multiplication. It all becomes really simple. Okay, that is just what I just told you. This is what I just told you. Very good. And of course, we should demand normal for this U to be a valid unit quantum gate. We do demand that the output states are normalized. Okay, so the coefficients A, B, C, D have to satisfy for any choice of E and F. As long as E and F themselves are a normalized state, then we demand that these coefficients A, C, B, D have to satisfy this relation. The output state must also be normalized. So with that condition, we have then guaranteed that this gate is a valid quantum gate. Okay. And we will see in a minute how to check that easily from just the numbers A, B, C, D. Okay. We won't need to actually do this for every possible state and calculate and make sure it's one. Okay. So we'll show that in a minute. That places, what it does is it places very stringent requirements on the coefficients ABC. Not any choice of ABCD will be a quantum gate. Okay. Okay, so in lecture 7, we showed that this was a valid quantum gate. Okay, just go back to your lecture 7 notes or look on the online on the video. We showed that this is indeed a valid quantum gate. We did that by taking this gate, operating on any general state AB, or EF, if you like, whatever you want to call that. And we showed that this gate satisfies that normalization condition. Okay, so that's already done. So now let's just represent that as a matrix, and also show you how to use Quirk to take this matrix and make it into a gate in Quirk. And then eventually we'll also be able to do it on IBM's thing. But since we're just doing the numerical stuff here, or the analytical stuff, I guess you would call it, we're not doing the experiments, we can do that here. So let me, okay, first of all, to represent as a matrix, we just follow our procedure. Okay. Here. So U, I know it probably flashed by too fast, but was basically this. So I took the coefficients when U was acting on 0, I put them here in the column. Okay, root 2 minus I over 2 and minus 1/2. And then U acting on 1 was just 1/2 root 2 plus I over. Oh, sorry, root 2 minus. That makes sense. I don't have to conjugate the diagonal. Okay, so that was our quantum gate, valid quantum gate. And so we represented it as a matrix. Okay. Is that okay with everyone? I just did follow the exact same procedure that we were talking with A, B, C, D, but now with like actual coefficients. Okay, now I can show you how to put that into code. And of course, you can use Python to calculate like numerical answers and stuff, but it's helpful to see it in the Quirk as well, because then you can use it as a gate, your own gate. Okay, so is it a show? Exactly. Okay, yeah. A little tricky. I have to like move things on this while trying to. And I have to share this. Okay. All right. So we see there, this is our Quirk website that I've shown you before. And now we can make our own gate. So you see that make gate button? You just press make gate, and I'd earlier been using it. So I've just input that same matrix. So root 2 minus I over 2 minus 1/2 and 1/2 square root of 2 plus, oh, that's a mistake, I should say. assuming this is just an order. Okay, and now it makes, oh, sorry, you know what? So that's our custom gate. I wanted to give it the name U, but let's. Oops. Oh. But anyway, if you can give it a name as well. So it should be, you can give it the name U. I forgot to do that. So we have this gate, and now we can see what it does when it acts on our state. So it's root 2 minus I over 2. These two are identical, which is what we wanted. This sort of gives you an idea, right? It's like, if you just take this element where it is in the complex plane, is what this representation is showing. So we know root 2 minus I over 2 is over here, but something seems wrong with these two. Like, wondering what's going on. Oh, I think after it makes it unitary, it must have made that change. Okay, I apologize. I didn't check this very carefully. Anyway, the idea is that you can now drag that gate in. For example, you can use some other gate, say a Hadamard after it, or Z gate before. And now you can start to see what it does by just dragging your gate in with other gates and see what comes out from code. Yeah, so that's one way to do it. Of course, the Python code, I showed you how to do it there as well. So those are two different ways you can check what Quark is doing. You can make sure that whatever we get out of Quark, we can trust it, okay? If it matches up with our calculations. And if it doesn't, there will be a mistake somewhere, most likely on our side, but there's always a possibility that there's something wrong with the way we entered it in Quark or something like that as well, so you can double check that. Okay. Oh, sorry. What to do? We now go back to PowerPoint. I have to check whether we can drag it out. Oh, sorry, you can see it. All right, I'm just going to stop this. Okay. Back to PowerPoint. Okay. So yeah, that was just to show you that you can see the same thing on Quark and on our Python code, for example. Okay, now what we can do is all of the 1 qubit gates that we had in the last class or the last couple classes, are just matrices. Okay. The first matrix that you should always know is the identity matrix. It's the wire in a quantum circuit. The wire means nothing is happening to your state. It just, whatever goes in comes out, right? That's what a wire does. So in our quantum circuit, a wire is the identity matrix. No matter what state I put in, I get the same state out. The identity matrix is just 1, 0, 0, 1. Okay, and you may also remember when we talked about gates, we introduced 4 basic gates, the I, the X, the Y, and the Z, and we said any gate U can be made up of some combination of I, X, Y, and Z. That's why we introduced them. If you don't remember, it's like a couple lectures ago, we wrote down some formulas using angles and so on for it. Anyway, what about the X gate? So remember, X acting on 0 gives me the 1 state, and X acting on 1 gives me the 0 state. It's basically a NOT gate, right? That's what X is. Well, again, in our language of whatever acts on 0, well, that's the 0, 1 column vector, right? Because it was 1, 0 into 0, 1, and then it made 0, 1 into 1, 0. So that's 0, 1, 1, 0. So those are the 2 columns of our X gate. Okay. And then the Y gate is the same idea. Y acting on 0 flips 0 to 1, but also gives you the phase I. Same with Y acting on 1 flips to the 0 state, but also adds in the phase minus I. So then just instead of 1s, I get I and minus I for the Y gate. The Z gate, as I've told you, has no classical analog, and that is just taking Z, it makes Z into Z, but adds a phase to the 1 state. So that gives me a minus 1 over here. Okay. And then we have the 2 other gates that we introduced, S and T. So S does nothing to the 0 state, but adds a phase I to the 1 state. And so that's 1, 0, 0 I. And T gate is the same, except the phase instead of being e to the I pi over 2 is e I pi over 4. So that's just repeated over here. And then finally, as I've told you, the most sort of useful and most utilized gate in quantum computing, which is the Hadamard, it takes the 0 state, produces the plus state, and takes the 1 state and produces the minus state. So that is just 0 produces 1 plus, so that's 1 1 in the columns, and then 1 minus 1 in the second column. So it becomes that easy now to write down all our gates and their operations. We don't need to give all these lists of things that they do. We just write down the matrix, and that gives us all the information we want. So, any questions before I move on about that gate mapping to matrices? So now we're going to compute this circuit using, we computed it once already in lecture 9 using standard Ket notation. That is, we took the state 0, operated with H, then with T, then with S, then with H, and then made a measurement. Okay. And it was okay, it was not bad, but it was involved. And you could imagine there are other gates which might be even more complicated that can make it much more. But with matrices, it's almost trivial. Okay. We'll compute it using matrix notation. The only thing you have to remember is that, which I have written here so that you don't get confused, the order of the matrices that we are using, that we are multiplying, will be reversed from the order in the circuit. That is, the leftmost gate appears as the rightmost matrix. Okay, and that's because of the way a matrix works in sort of a time sense, which is the state 0, the first gate that acts on it is H. Okay. So the first output of here is H times 0. Then T acts on that, so that's T times H times 0. Then it's S, so that's S times T times H, and then it's H again. So the final state is H, S, T, H acting on 0. Okay? So that's why the leftmost gate appears as the rightmost matrix. Okay, so let's write down our matrices first. H, which I just flashed on the previous slide. So I'll have a look at it here. H is the matrix, 1 over 2. This is the plus state from 0 and the minus state from 1. And then S is 1, 0, 0 I. T, the same as S, except it's 0 e to the I pi over 4. If we need anything else, that's H, S, T. I think that's it. Right? Yep. So the output of this gate, of the circuit, is H, S, T, H acting on the state 0. That's what we want to compute. Okay. So we do that with the matrices. So the first column vector is just 1, 0, because that's the state 0 over here. The second is our first matrix, which is H, which is 1 over root 2, 1, 1, 1 minus 1. Then we have the T matrix, which is 1, 0, 0 e to the I pi over 4. Okay. And all right, I'm going to leave these last two for later because I'm out of space. So let's just first compute this guy over here. Okay. What do I get over here? H acting on 1, 0. What do I get? What? Yes.
I'm gonna give you the plus there.
Yes. And what is that? In this.
1 over root 2. 1.
Very good. So that gives me 1 over root 2 times 1. Everybody see that? Okay. So that is H S. And now I take my next matrix 1, 0, 0 e to the I pi over 4. Okay, I'll compute that over here. Here. Who wants to tell me what the output of that matrix is? That gains. Yes?
So 1 over rad 2 times 1 e to the I pi over 4.
Yeah.
Yeah,
You got it.
1 over root 2 on the
Okay.
other side, yeah.
Excellent. Yes. H S times. So I mean, so scalars like 1 over root 2, when they multiply column vectors, you can just take them out because they are just multiplying everything. So I'll put the 1 over root 2 out here. Don't need to worry about it anymore. Okay, everybody okay with that step? It's a scalar, I can just take it out of everything. So 1 over root 2 HS and E1 e to the I. Again, by the rules of matrix multiplication, we can see that. So 1, 0 times 1, 1, which is 1 times 1 plus 0 times 1, so 1. And then 0 times 1 plus e to the I pi over 4 times 1. So that gives me the pi over 4, e to the I pi over 4 in the second element. Okay, now we just carry this through mechanically, right? There's no thinking here. It's just calculating. Okay, what about this? I think it won't be too difficult for you to figure out. This is same I e to the pi. Right? The same rules. And then the only one we have to think about now is a little bit this one. So, and then there's a 1 over root 2, of course. So that gives me 1 over root 2 times the final column vector space is 1 plus 1 times 1. So I'll write it out if you like. 1 times 1 plus 1 times e to the I pi over 4. That's in the top element. And then the bottom element is 1 times 1 minus 1 times I to the I pi over 4. That gives me 1 over root 2, 1 plus I to the I pi over 4, and 1 minus I e pi over 4. And now, if I wanted to write this as an actual state, output state psi, right? I would write this as 1 over root 2, 1 plus I e to the I pi over 4 times the state 0 plus 1 over root 2, 1 minus I pi over 4, I e, 1 minus I e, I pi over 4. State. What? Now, of course, you could also make this I as e to the 3 I pi over 2. Oh, did I make a mistake?
So,
Yeah, I think there's a second one override too.
Then 1 over. Oh, thank you. Yes. Yes. That came from the Hadamard. Didn't I? Thank you. Good. Glad to see you. You're all paying attention, awake. Friday afternoon. Okay, excellent. And so yeah, like I was saying, I is just e to the I pi over 2. So I could also just write this as 1 plus e to the I 3 pi over 4 and 1 minus e to the I 3 pi over 4. Okay. So all of I can be replaced by I 3 pi. I wanted to make it a little simpler looking. And this is exactly the state that we had when we calculated it by hand a couple of lectures ago, or maybe one lecture. And yes,
With those,
you need to see it again.
no, it's okay. If you did the matrix multiplication on the gates,
Yeah.
you like compose a gate.
Yes.
That represents.
Absolutely, correct.
Okay.
Absolutely. So what you're saying is instead of like multiplying it on h on 0, 1, 0, and then etc. If I just multiply the matrices themselves, which I can do with the same rules of matrix multiplication, then I'll get some final matrix. And that matrix indeed will be a gate, which is an equivalent. So you can replace all of those 4 gates with just one gate, which has that matrix. Absolutely. And that's how we prove circuit identities, basically, which I'll show an example of in a minute. Okay. So there are lots of gates that look different, but really, if you compose them with the matrices, you find that they're identical. Right? So, yes.
This is kind of a common dark, but like for the matrices representing gates, are they like, do they have to be non-linear?
I'll give you some conditions on the gates themselves.
Okay,
Not every matrix is a gate.
gotcha.
Yeah, not every 2 by 2 matrix is a gate. That will be in a minute, couple minutes. Any other questions? This is great. Thank you. Keep them coming. Okay, I just did that matrix calculation by hand. And this is the result from lecture 9, which is also the same. Okay, and we can do this in Python. Okay, so sorry, it showed up a little small. I was just cutting and pasting from my Python code. So you'll have the slides, so you can see exactly what this is. You can input it yourself, and you can check that this is indeed the answer. Okay. So basically, I just, the only thing I do is I like to just define, the complex number 0 plus 1.0j. I just define that as a capital J, just to make my own life easier. Because sometimes it'll complain that J is something it doesn't know in Python, okay? Unless you define it specifically like this number, okay? Oh, by the way, J instead of I, this is an electrical engineering convention. For those of you who are electrical engineers, so you know this. And so I is just something, because it's current, right, in electrical engineering often. So you get confused if you use I for that and complex numbers. But so J is often used, but it doesn't really help in physics because we use J as well for other things. But I'm using that convention, and it's also what's in NumPy, so we'll just use that here in Python. Oh, and so yeah, that's exactly what I did. I just did matrix multiplication of HSEH, and I get an array at the end, which is the two components, and then to check that that is indeed our answer, I took our the value that I just found, and I just computed that, and I get exactly the first element of this array. Okay. And the second element similarly is that minus the e to the I pi over 4, and that gives me this element over here. Yes?
Is there a better way of checking your answers with Python? Because I feel like if you have to like know what the answer is, like check it against itself. Like,
Yeah, I mean, there is no other better way in Python at least.
oh,
I mean, there is a SymPy. So you might want to play with that package. I haven't used it that much. So SymPy allows you to do like symbolic calculations. So then instead of giving you an answer with like lots of numbers, I think it tries to like make it look more, symmetric, basically.
Oh.
Yeah. But I'll just show you on the next slide, the Mathematica code. So this is what I end up using for symbolic calculations a lot. Okay, so it's the same thing, exact same thing. Of course, the two don't have the same conventions on how they define matrices and functions and the brackets and the square brackets. So this is a pain, like every programming language. But it's the same idea. I define a zero state, just 1, 0 as my column vectors, and then here are the matrices H, S, and T. And the nice thing about something like Mathematica is it understands, exponentiation of complex numbers, without having to numerically do it all the time. Like it keeps it, as you can see, as e to the I pi over 4, so that you can now compare it to your algebraic answer. Okay. So that's a nice thing with Mathematica. Yeah, so I think I made a mistake here. So sorry. When I was writing the formula out in LaTeX, this is I e to the pi over 4, not I e to the 3 pi over 4. Okay. And you can see that agrees as well with Mathematica. Okay. Okay, now we can do circuit identities. Just going back to the question you were asking, Richie, is, if I write down some string of gates, can they be shown to be equivalent to some other gate? And that's exactly what this is. So now I remove the sort of, this constraint that I'm multiplying the gate with some column vector. I assume there's a column vector at the end that I'll operate on, but I don't need it. I'm just looking at whether two matrices are identical. So H times X times H. Okay. Once again, you write down the matrix for H, the matrix for for X, and then the matrix for H again. And all it is just carrying out the matrix multiplication. So I'll just pull that 1/2 out here. It's 1, 1, minus 1. Then here, so this is 0 times 1 plus 1 times 1, so that's 1, right? And then 0 times 1 plus 1 times minus 1, minus 1, okay? And then 1 times 1 plus 0 times 1, that's 1. 1 times 1 plus 0 times minus 1, that is 1. Okay. Clear, didn't mess it up. The proof will be when I find the final answer. So 1/2 times. Okay, now once again, 1 times 1 plus 1 times 1, that's 2. Good. 1 times -1 plus 1 times 1, that's 0. Okay. 1 times 1 plus -1 times 1, that's 0 as well. Then 1 times -1 is -1, -1 times 1 is -1, that's -3. So cancelling out the factors of 2, you get 1, 0, 0 minus 1, which if you look in your table is the Z gate. Okay. And this is the proof of many circuit identities. So you'll do a couple in your homework. Okay. But that's what this is. Questions about that multiplications? And of course, you can put it into Mathematica or Python and just verify it that you didn't make a mistake. That's the nice thing about matrices. We got a bit delayed with all that. Oh, yeah, actually. So I just did the same thing with on Mathematica. So H, I define X, and then H, H, that gives you the same answer. So calculations. Okay, so in the last few minutes, I'll just introduce the concept of unitarity. This speaks to the question that Richie had that, is every matrix a good quantum gate? The answer is no. It has to satisfy a condition, which we will now derive. I don't know if I'll finish the derivation, but we'll see. Okay, so we saw this earlier in today's lecture. We take any state psi, which is EF, right? Some arbitrary state. We operate with the state U, the matrix U on the state set. Okay. And we got this result. And we said one way to make sure that this is a valid gate is to verify that for all combinations EF, any number E and F, that these are normalized, meaning norm squared of this plus norm squared of this is 1. This is obviously not a simple thing to do in every case. So we want to derive something a little bit easier to verify. Okay. So we'll see now that this condition that these coefficients have to be normalized for any choice of E and F actually places a strict limitation on the types of matrices that we can use for quantum gates. Okay. So let's look at this column vector over here. Okay. This is the column vector of U acting on any state psi. Okay. So I could call this some new column vector, new state. Let's call it phi, right? Instead of phi, I'm going to call it something that kind of reminds us that this state is not just any state. It came by taking the operator U and acting it on the state side. So this is a new column vector. I could have called it anything, alpha, beta, gamma, whatever, or phi. But instead I'm going to call it, don't get confused by the notation. It just means, remember that this column vector came by taking U and operating on the state side. It's just some new column vector. Okay. I could have called it alpha, maybe, but I just want to remind you that it's always found by taking U and acting on the state side. But remember that to every state in the Ket space, there must be a dual, right? The bra vector. So we want to find the bra that corresponds to the state that we just wrote down, which is Ket U psi. Okay. What is this state? Well, it is just found, it is just found by taking this column vector and finding its conjugate transpose, right? So a row vector with the conjugate of each of these elements. Okay, everyone okay with me here? So that's what I wrote down in the next slide. Sorry, for now, ignore this last. Something happened to the animation. Anyway, so just look at that. That's the column, that's the row vector and the transpose. The conjugate transpose of that column vector that we just wrote. So I took the first element and I took its complex conjugate. Second element, its complex conjugate. Just put this in the row vector form. Okay? And I claim, which you can verify easily by doing the multiplication, that this can be written as this row vector E star F star times this matrix over here. Okay, let's do the math. It'll be pretty obvious. E star times A star plus F star times C star must be this guy, which is exactly what it is. E star times B star plus F star times D star must be this guy, and it is. So they are identical. These two expressions are identical. Okay? But E star, so I'm just writing that same expression down here. Okay, just exact same thing. So I've written that the bra U psi equals the row vector E star F star times a matrix which is A star, B star, C star, D star. So this bra vector U psi, and remember E star F star is just the bra psi, because the ket psi is EF column vector. Okay, so the dual to psi, the column vector, must be the row vector with E star F star. So that's this first thing over here, the bra psi. And the second one I identify as a matrix which I call U dagger. We've introduced this dagger operator before. What it means is finding the complex conjugate transpose. So if I took A, B, C, A, if I go back a second, let me see. So let me just write it down again. Let me just very clearly define it. U dagger is the matrix A star, B star, C star, D star. And if you look at the original matrix U, over here, A, B, C, D, if I take its complex conjugate transpose, I get A star, B star, C star, D star. So U dagger is this matrix over here. A star, B star, C star, D star. I mean, finding the transpose is just, I just interchange the off diagonal elements, right? So just taking U and interchanging its off diagonal elements, and then taking the complex conjugate of all the elements. So that's this matrix U dagger. So far what I've shown you is the state U psi, which I wrote a couple slides ago, has a dual, which can be written as the dual of psi times the complex conjugate transpose, which is called U dagger of the matrix U. Okay, the dagger of the matrix U. And this complex conjugate transpose has a name in quantum physics. It's called the Hermitian adjoint. Okay, so sometimes I might by mistake say the adjoint, but it just means complex conjugate transpose. Okay. So let's go through the steps. We have calculated the dual to U psi. And remember, we demand that U psi state should be a valid quantum state, normalized to 1. Therefore, its inner product with its dual must be 1. So that's our demand. That is the condition we must satisfy for U to be a valid quantum gate. That U acting on any state psi must give me a valid quantum state, means that U psi, that new state that we form, must with its own dual give an inner product of 1, be normalized to 1. Everybody following me here so far? It's a little bit complicated, but the steps are logical, but it can take a little bit of thinking just to make sure that you're following what is the dual and what is the dagger and all that stuff. But okay, we just showed U psi, this state is U times psi. Okay, let me just explicitly write all that. Just give me one more minute and we'll be done. So the definition of the state U psi is just U times psi. Okay, this is just the definition. That's how we define it. Okay. And we have just shown that its dual U psi is the dual of psi with U dagger acting. Okay. So the row vector psi times row vector meaning complex conjugate transpose, of course, times the U dagger Hermitian adjoint. Therefore, the demand, now we demand that for any state psi, U psi inner product with itself must be 1. Which means psi U dagger, that's from this part, and U psi from there is just U times psi must be 1. Okay, this must be true for every state psi, no matter what state it is. So the only way I can satisfy this is by demanding U dagger U be the identity operator. Is U dagger U must be the identity matrix. You can also run this whole thing in reverse and show that U dagger must also be the identity. Okay. That is, start with the state U dagger, start with the matrix U dagger, act on the state psi, find its dual, and then take the inner product. You get U dagger must be I, because the Hermitian adjoint of a matrix, they are exactly dual to each other. So finding again the complex conjugate transpose of the complex conjugate transpose will give me back the matrix. So U dagger must be I. Okay, that pretty much, let me just finish by summarizing that on the last slide. We're done. So such matrices which satisfy this condition, U dagger U equals identity and U dagger equals identity too. They're equivalent to each other. Such matrices are called unitary matrices. Okay, and all quantum gates, by our proof, have to be unitary matrices. And any unitary matrix, by conversely, is a quantum gate. As long as I can write down a unitary matrix, it is some quantum gate. Okay. All right. I'll finish there. And just to conclude, I had some more, but I'll come back to this next class. So today's lecture, we've talked about change of basis using matrices, quantum gates as matrices, and we've introduced this very, very central and important concept, showing that all quantum gates are unitary matrices. That is a very strong condition which allows us to filter out any gate, any other matrix that doesn't satisfy those conditions. Okay, thank you and have a good weekend. See you next week.